Hello viewers, this is indeed a great pleasure for me to bring to you another program in the Teleschool Senior Series. The subject today is vector equation of planes. Now we can express planes in various forms, in vector forms or dot product form or Cartesian form. We will see the scalar product form of equation of plane. In this form, the equation of a plane is expressed as follows: r dot n equal to d, where r is the position vector of a general point which we express as xyz on the plane. That is, expressed in terms of column vectors, r is x, y, z. N is a vector which is perpendicular to the plane. Generally, we will express n as the column vector ABC. D is a real number. So there are three terms in the vector, in the equation of plane, in the scalar product form: the position vector, the vector perpendicular to the plane, and the real number. If we want to express the equation of a plane in Cartesian form, we simply have to replace n in terms of the vector and then carry out the dot product. So the scalar product form of the equation of the plane was r dot n equal to d. If we replace r by x, y, z, that is the position vector of the general point on the plane, and the vector n by ABC, and then carrying out the dot product, a times x plus b times y plus c times z, we obtain ax plus by plus cz equal to d. Note that this is the Cartesian form of a plane. This is the scalar product form or dot product form of equation of a plane. In the Cartesian form, the coefficients of x, y, and z represent our entries of the vector perpendicular to the plane. To write the vector equation of a plane, or the equation of a plane in general, we require at least three non-collinear points on the plane. That is, three non-collinear points must be known on the plane, or two non-parallel vectors on the plane must be given. So let's see how to write the vector equation of a plane. Suppose that three non-collinear points are known on the plane. Point A having coordinates x1, y1, z1, point B x2, y2, z2, point C x3, y3, z3. And we want to write the equation of the plane P. So ABC are three non-collinear points lying on the plane P, and we would be finding the equation of the plane P. Suppose that n is the vector perpendicular to the plane. N is the vector which is perpendicular to the plane. And since it is perpendicular to the plane, it will be perpendicular to the vector AC and to the vector AB. Now, since A has coordinates x1, y1, z1, B has coordinates x2, y2, z2, therefore the vector AB can be expressed as x2 minus x1, y2 minus y1, z2 minus z1, which is a1, a2, a3. We will use this notation rather than this one. It will be more convenient. AC similarly can be expressed as x3 minus x1, y3 minus y1, z3 minus z1, or more conveniently we'll write AC as b1, b2, b3. So we have three points on the plane, A, B, and C, or two vectors, AB and AC, which we have written as A1, A2, A3, B1, B2, B3. So naturally, the first step would be to find the vector perpendicular to the plane. That is the vector n. Let's see how to find the vector n. So the vector AB was expressed as follows: A1, A2, A3, B1, B2, B3. To find n, we carry out the following determinant. The first row are the unit vectors I, j, and k. The second row is one of the two vectors on the plane. It could be a1, a2, a3, b1, or b1, b2, b3. We have chosen to write a1, a2, a3 first. And then the third entry in that determinant is the second vector. Now, to carry out the determinant, we split it. I times the determinant of the matrix obtained by deleting the first row and the first column. What remains would be a2, b2, a3, b3. Minus j times the determinant of the matrix obtained by deleting the second column and the first row. Therefore, minus j times a1, b1, a3, b3, plus k times the determinant of the matrix obtained by deleting the first row and the third column. That is k times a1, a2, b1, b2. These are determinants of 2 by 2 matrices, which can be obtained by multiplying elements on the main diagonal minus product of elements on the super diagonal. That is I times a2 times b3 minus b2 times a3. We have simplified the determinants of the 2 by 2 matrices for you, so that I is a2 b3 minus a3 b2 minus j times a1 b3 a3 b1 k times a1 b2 minus a2 b1. Since a1, a2, a3 are numbers, all this can be expressed as numbers, which we have done here. Suppose that this is equal to a, this is equal to minus b, and this is equal to c, so that the vector n can be expressed as a, b, c. Once we have found the vector perpendicular to the plane, that is the vector n, the next step would be to find the real number, the value of the real number d. Now, in the scalar product form, the equation of a plane is expressed as r dot n equal to d. We take any point lying on the line, say the point A, which had coordinates x1, y1, z1. We replace r by the position vector of this point. That is, r can be expressed as x1, y1, z1, dot n. N is the vector perpendicular to the plane. Carry out the dot product, a times x1, b times y1, c times z1, and find the sum to obtain d. So d is obtained by replacing r in the equation by the position vector of a known point on the line. Let's take an example. Write the equation of a plane passing through A, which had coordinates 1, 1, 1, B, 2, 1, 0, C, 2, 2, minus 1. The first step would be to find two vectors on the plane. Vector AB, which is B minus A, 2 minus 1, 1 minus 1, 0 minus 1. Vector AC, C minus A, 2 minus 1, 2 minus 1, minus 1, minus 1, 1, 1, minus 2. The next step would be to find the vector perpendicular to the plane ABC. So we express it as a determinant. The first row would have as entries I, j, k. The second row, one of the two vectors lying on the plane. We have chosen to write AB first, 1, 0, minus 1, AC, 1, 1, minus 2. We evaluate that 3 by 3 determinant. It is I times the determinant of the 2 by 2 matrix obtained by deleting the first column and the first row, which remains 0, 1, minus 1, minus 2. Minus j times the determinant of the matrix obtained after deleting the second column, and the first row. That is minus j times the determinant of 1, 1, minus 1, minus 2, plus k times the determinant of the 2 by 2 matrix obtained by deleting the first row and the third column. That is determinant of 1, 0, 1, 1. So the next step will simplify the determinant of these 2 by 2 matrices to obtain the vector which is perpendicular to the plane. So simplifying the determinant of the 2 by 2 matrices, we obtain the following vector: I times 1, j times 1, plus k times 1. That is, the vector perpendicular to the plane ABC is 1, 1, 1. The next step would be to find the value of the real parameter d. So d is r dot n. We can replace r by the position vector of any one of the points lying on the plane. We have chosen the point B. So we will replace r by the position vector of B, which is 2, 1, 0, and carry out the dot product of B, position vector of B, and n. 2 times 1, 1 times 1, 0 times 1. Evaluate the sum to obtain 3. Therefore, we have obtained the vector perpendicular to the plane ABC as 1, 1, 1, and the value of the real parameter d as 3. So replacing n and d in the equation of plane, we obtain the following: r dot n equal to d. N was obtained as 1, 1, 1, and d as 3. Or if you want to express it in Cartesian form, we just have to replace r by x, y, z, and carry out the dot product to obtain x plus y plus z equal to 3. So this is the equation of the plane in scalar form, scalar product form, and this is the equation of the same plane in Cartesian form. We can say that this is the equation of the plane in dot product form or scalar product form, and this one the Cartesian. It's very important to verify whether a point lies on a plane or not. Let's take an example. Does the point having coordinates 7, 4, minus 2 lie on the plane having equation r dot 1 to 5 equal to 8? Note that 1 to 5 is the vector perpendicular to the plane. So the first step would be to evaluate the left-hand side of the equation of the plane by replacing r by the position vector of the point. So we'll replace r by the position vector of the point, 7, 4, minus 2. We carry out the dot product. 7 times 1, 4 times 2, minus 2 times 5, which gives us 5, which is not equal to the right-hand side of the equation of the plane, which was 8. We have obtained 5. Therefore, the point A does not lie on the plane. Now, let's take another example to verify whether a line lies on a plane. Suppose that we have a line L and a plane P. Line L has equation I plus 2j plus k plus t times 2i plus j. We can express it as follows: 1, 1, 2, 1, which is the position vector of a known point on the line, plus t times the direction vector of the line, which is 2, 1, 0. Simplifying the right-hand side, we get 1 plus 2t, 2 plus t, 1 plus 0, which gives us 1. The equation of the plane is r dot I minus 2j plus 2k equal to minus 1. So in order to verify that whether the line lies on this plane, we replace r by this expression. So this is what we'll carry out. We'll carry out the dot product by replacing 1 plus 2t, 2 plus t by r. The dot product gives us the following: 1 plus 2t minus 2 times 2 plus t, 1 times 2. That is 1 plus 2t times 1, 2 plus t times minus 2, 1 times 2, where r, this expression was obtained from the equation of the line, and this is the vector perpendicular to the plane. Of course, if the result of this dot product would be minus 1, which is the right hand side of the equation of the plane, we'll immediately conclude that the line lies on the plane. If the result of this dot product is not minus 1, then we'll conclude that the line doesn't lie on the plane. In fact, carrying out the dot product, we found that yes, the dot product has a value of minus 1, which is equal to the right hand side of the equation of the plane. And this leads us to conclude that L lies on the plane. It's also very important to be able to find the angle between a line and a plane. Let's consider the following diagram. Suppose that I have a line L which has equation x1, y1, z1 plus t times a1, a2, a3. So x1, y1, z1 is the coordinates, the position vector of a known point on line, and a1, a2, a3 the direction vectors. Suppose that I have a plane and the vector n is the vector perpendicular to the plane. And suppose that theta is the angle between the line and the plane. Now, since n is a vector perpendicular to the plane, this angle is theta, this angle is 90 degrees, therefore this angle will be 90 minus theta. So instead of finding theta, the angle between line and plane, we would find the angle between line and the vector perpendicular to the plane. That is, we'll find 90 minus theta. So if theta is the angle between line and plane, 90 minus theta would be the angle between the direction vector of the line and the vector normal to the plane. So again, we'll be using dot product to find the angle between the line and the vector perpendicular to the plane. So cos of 90 minus theta. As I said, we won't find theta first, we would find 90 degrees minus theta, which is the angle between the line and the vector perpendicular to the plane. Cos of 90 minus theta is obtained by applying the dot product on the vector, on the direction vector of the line and the vector perpendicular to the plane. Note that we can replace in this formula cos 90 minus theta by sine theta. So instead of writing cos 90 minus theta, we would write sine theta. Let's take an example to illustrate this concept. Find the angle between the line. Having equation r equal to minus 1, 2, 3 plus s times 2, 1 minus 2. The direction vector of the line is 2, 1 minus 2, whereas the vector perpendicular to the plane is 2, 3 minus 7. To find the angle, we'll find the angle between the direction vector and the vector normal to the plane. And we would replace it by sine theta. So sine theta is dot product of vector normal to the plane, 2, 3 minus 7, and the direction vector of the line, 2, 1 minus 2, divided by the magnitude of each one of them. We obtain 7 over root 62. Taking the sine inverse, we obtain theta as 63 degrees to the nearest degree. It is also very important to be able to find the angle between two planes. Suppose that we have two planes, P1 and plane P2. Then the acute angle between plane P1 and P2 would be equal to the acute angle between N1 and N2. Therefore, again, we will use dot product to find the value of theta, which is the angle between the two plane. Cos theta would be n1 dot n2 divided by magnitude of n1 times magnitude of n2. And we would take the modulus in order to obtain the acute angle between the planes. Let's take a simple example to illustrate. Suppose that we have two planes, P1 and P2, having equations r dot 213 equal to 6, r dot 231 equal to 9. Therefore, the vector normal to plane P1 is 213, and the vector normal to plane P2 would be 231. So we have n1 and n2, 213, 231. We use dot product. We apply dot product rule on these two vectors, which are the two vectors perpendicular to the plane. Applying the dot product gives us 213.231 divided by the magnitude of 213 times magnitude of 231, which gives us 5/7. Taking the cos inverse, we obtain theta as 44 degrees. So the angle between two planes, the acute angle between two planes, is the acute angle between the two perpendicular vectors to the plane. That is, we apply the dot product rule to n1 and n2 to find the angle between the two planes. Let's find the shortest distance or the least distance from a point to a plane. Suppose that we have a plane having equation r dot abc equal to d and point A having coordinates x, y, z. So we will not entangle in the derivation of this distance. The distance is given by the following: d, which is the value of the parameter in the equation of the plane, ax plus by plus tz, where a, b, c are elements of the vector normal to the plane, and x, y, z are the coordinates of the point. So the distance between A and the plane is L, and L is given by this formula. Let's take an example. Suppose the coordinates of A is 4 to 1, and the equation of the plane is r dot 2, 1 minus 2 equal to 13. So in this example, value of x is 4, value of y is 2, value of z is 1. Elements of the vector perpendicular to the plane, ABC, are 2, A is equal to 2, B is equal to 1, C is equal to minus 2, and D is equal to 13. Replacing it in our formula, we obtain D, which is 13, minus A times X, 2 times 4, plus B times Y, 1 times 2, plus C times Z, minus 2 times 1, divided by square root of A square, B square, C square, which gives us 5/3. Therefore, the perpendicular distance from point A to the plane is 5/3 units. So this was the shortest distance from a point to a plane. We will also look at how to find the point of intersection of a plane and a line. Suppose that I have a line R having equation R equal to 1, 1 minus 2, T 1, 0, 5, and a plane having equation R dot 2i plus j minus k equal to 2, or R dot 2, 1 minus 1 equal to 2. To find the point of intersection of line and plane, the best strategy is to solve simultaneously. So we would replace R in equation of plane by the following expression obtained from the vector equation of the line. That is, we replace R by 1 plus t, 1 minus 2 plus 5t, and carry out the dot product. So this is equal to 2. 1 plus t times 2 plus 1 times 1 plus minus 2 plus 5t times minus 1 equal to 2. Simplifying, we obtain t is equal to 1. Therefore, t is equal to 1 defines the point of intersection of line and plane. So we will replace t by 1 in this equation, in the vector equation of the line, in order to obtain the position vector of the point of intersection. So replacing t by 1, we obtain r equal to 1 plus 1, 1 plus t, which is 1 plus 1, equal to 2, 1 minus 2 plus 5t, minus 2 plus 5 times 1, which is 3. So this is the position vector of the point of intersection of the line and the plane. In terms of coordinates, we'll say that the point has coordinates 2, 1, 3. Next, we'll see how to find the point of intersection of, or the line of intersection of two planes. Whenever two planes meet, they will have a line in common. How to find the equation of this line? Suppose that we have two planes having coordinates r dot 1, 1, 1 equal to 3, or expressed in Cartesian form x plus y plus z equal to 3, and a second plane having equation r dot 1, 2, 3 equal to 5, or x plus 2y plus 3z equal to 5. This is the line of intersection. How to find the equation of the line of intersection? The first step would be to express the equation, both equations of plane, in Cartesian form, and then we'll be solving them simultaneously. Note that we have three variables, x, y, and z, and two equations. So the first thing to do would be to eliminate one of the equations. We have decided to eliminate the variable x. So subtracting equation 1 from equation 2, we obtain y equal to 2 minus z. What we'll do will be to replace y by 2 minus 2z in equation 1 to obtain x in terms of z. So what we did was eliminate x first in order to be able to express y in terms of z. Replacing this expression back in one of those equations, we obtain x in terms of z. And then the next strategy would be to say, suppose that z is a parameter t, because z was the surplus variable. We had two equations in three unknowns. So expressing z as t, we obtain x as 1 plus t and y as 2 minus 2t. So we would replace x, y, and z in terms of t in R to obtain R equal to x, y, z, or 1 plus t, 2 minus t. Separating them into two column vectors, we obtain the equation of line of intersection. So viewers, this brings us to the end of today's program. In this program, we have considered the equation of plane in two forms, the scalar product form and the Cartesian form. We have also seen how to verify whether a point lies on the plane or a line lies on the plane. We have also seen how to find the point of intersection of line and plane, the angle between line and plane, and the angle between two planes. And finally, we also saw how to find the equation of line of intersection of two planes. Thank you for watching us. Until next time, it's goodbye from us.